I'm going to try and put the flight back into this flight software thing. I'm not a coder. I'm a systems engineer at the Aerospace Corporation, and I spent a few years back about a decade ago working in an organization called the Cross-Program Research Office, and one of the things that we did as part of that was cross-program studies, and my domain was on-orbit anomalies, failures, bad days for a lot of people. And in looking at failures, mission failures across like about a 30-year window, there was a little theme that came about. And so this Test Like You Fly process, this isn't just, you know, somebody's interpretation of what Test Like You Fly might be. This is a codified process that we've been working on since 2008 with people in industry like Lockheed and Boeing and ULA and like that. So this is a work of a lot of people. And why we're here today is because about 3 months ago, I got a call from a program office down the hall from me saying they were charged with trying to deal with Test Like You Fly in the software, and they didn't quite know how to do it. And I'm looking at Karen here because Karen was also working this project. And we thought we were going to do a paper today that was reflective of that particular project. But because of the shutdown, we wound up not having enough time to really do that. So what you're going to see here is mostly a very condensed version of a tutorial that we teach at the Aerospace Testing Seminar. So if this is at all of interest to you and you don't get enough of what you need here, I'll give you information about how to sign up for the ATS. Now, where's my, do you have a pointer? He didn't hand me one, so we have to do it. No. There we go. Okay, so what I hope to do today is, as you all probably know, a lot of the Test Like You Fly escapes are related in some way to software. We have not all that many hardware failures, out-and-out hardware failures. What we typically see are, you know, the thing that the gentleman before me was just talking about, like the subtle error that gets away from you and shows up in flight. Actually, a lot of them are not subtle at all. They are dirt stupid. And some of them come about late in the game, and some of them are a hardware-software mismatch, or somebody did something wrong in the hardware and nobody told the software people about it, and so the software didn't have an opportunity to correct the hardware problem. So we have those kind of things. And earlier talks today were already talking about the kinds of errors that do show up. You're all familiar with these. One of the other things about software is that when people finally get around to saying, oh, yeah, I could do a test that is kind of like how we do operations, but I can't do it on the flight vehicle because the flight vehicle, oh, thank you, is not available. It's valuable time. I don't want to break it. So we'll have to do that kind of test, I don't know, somewhere else. How about on that software test bed? And so a lot of times the software people will inherit the Test Like You Fly, or what we came to call the Like You Fly tests. So we speak like Yoda somewhat. So this is going to be a very brief overview of how do you get down to figuring out what looks like what you fly, how you fly at the flight software level. Nope, that's not the way I want to go. That's where I want to go. First of all, we start off with, and some of you people, especially from JPL, might think of Test As You Fly. We stopped using that early on because that was a confusion, because you really can test as you fly. We launch CubeSats as tests. We do flight tests. So this is before launch. And this is a principle. The first principle there was stated in a paper by Dave Shelton of Lockheed back more than a decade ago that said, don't do anything for the first time in space if you can help it. You'd really like to do those things ahead of time because the most likely time to fail is the first time you try something. We encountered a lot of people who said, well, I don't want to do that because I'm going to break the system. You know, we can't do a lot of the things that are like you fly in a one gravity atmosphere kind of environment. So the point here is not to do anything damaging intentionally. The other part about tests like you fly, this isn't meant to replace anything else. All the kinds of tests that you've been talking about for the whole part of this conference, that all still applies. It doesn't go away with adding on tests like you fly. This is just an approach to trying to narrow down the test cases, the use cases that you're faced with. You know, you have potentially hundreds, thousands of tests that you could do, and you don't have the time or resources to do them. So this is going to be a way to help narrow that down, we think. And there's a part of this that also says it's not just what you do in test, it's what you don't do in test that could pose a risk. There are some legitimate things that you cannot test before you fly. Got it. I don't have the time, I don't have the resources. It's just not really practical or feasible to do these kinds of tests. But it's not okay to say, I can't do it, I'm done. It's to say, like, what am I going to miss? You all know the kind of errors that can creep into this stuff, and you need to know where they could be. And so there are things that you might say, I can't validate that this kind of error isn't there because I couldn't do the test, but I can know that there's that kind of error, and I can ask, does that kind of error lead to something fatal on the mission? When we talk about failures, we mean these things that happen right away. This is a day of launch or within a day of launch effect. This isn't, there's a term that people use sometimes that's called infant mortality. This isn't about infant mortality like a part failure. This is about something is wrong because you didn't catch it. This is pretty much always an escape from the test program. Sometimes things happen a little later, and that's because it's the first time you do something. There are some things that don't happen for the first time until very late in the game. And I'm not going to talk to you people at this conference about the Mars program failures. I'm sure you're more than thoroughly familiar with them. But I do want to point out that this is something that happens in a hurry, and they are catchable if you think about them, we think. So the process that we put together, and why we call it a process, not a test, is that most of what we are looking at are really a specific kind of application of the system engineering processes that people do anyway. I just realized I probably have a laser here somewhere. Nope, that wasn't the one I wanted. Okay, so the system engineering things, you can't test like you fly till you know how you fly, so you need to characterize the mission in a way that you can translate into test terms. And so we have identified some artifacts that how to characterize the mission, and we call them, take a breath for this, first-time events. So you go looking for things in a mission timeline that will tell you when you're going to do some activity for the first time. We borrowed something from the JPL team back in the Mars program that we're calling a mission critical fault analysis. This is doing the failure analysis before the failure. I'm going to show you that just a little bit later on, but it is a fault analysis top down. You're going to take those things about characterizing the mission and where you're going to go actively looking for faults and map those things into what we call the like you fly tests. Those places where you can't do it or can't do it well, you need to do some risk management and say, look, we eyes wide open aren't going to do this test, or we can't include certain characteristics of the mission in a like you fly test, and so we're going to have to either carry the risk or go and find those potential flaws in some other manner to assure ourselves that we're okay. Okay, so this is a lot of words. I'm going to stand on it just to remind myself what I put up here. Okay, one of the things about the test like you fly philosophy that process that we had to incorporate is the notion of pyramids. Most people are kind of familiar with the physical integration pyramid. We found you needed to deal with a couple of others. One is the mission timeline pyramid, and the other is a supplier pyramid. And all these things come from lessons of failures. When we do the fill-up tutorial, we spend a lot of time telling stories, and unfortunately, in the 35 minutes I have here, I don't have time to tell stories. But if anybody's interested, we can talk a little bit afterwards. This is the standard pyramid, and what I'm going to talk about is that a lot of things that about Like You Fly is, Like You Fly is a satellite issue, or is a satellite ground system issue, or it's a constellation issue, depending on where you're at. So the right place to test that is at the highest levels of this pyramid. Practically speaking, you're limited in what you can do at those levels as an integrated vehicle. So very quickly we come down the pyramid and we land in the lap of the software subsystem as a CSCI. So that's where we're going with this one. But we also have time. I was really glad to hear the first talk of the afternoon, the gentleman from Southwest, talking about needing to characterize time, because that's the real important thing here. It's the thing that a lot of our testing ignores. You know, we test functions, we test performance, we test compatibility, we do those kind of things, but we tend not to put it on a timeline, on a clock that doesn't stop. I've seen tests run where people say, like, okay, I'll do a day in the life test, and they'll do, like an orbit, low Earth orbit, and you're running around 90 minutes, and you come back 90 minutes later, and you reset the clock back to 0. But in flight, we don't reset the clock. The clock keeps running, and things keep happening, and things keep accumulating. And all afternoon, I've been hearing from the various people presenting all the different kinds of errors that can happen, including these accumulation errors and things like that. So if you're not running a test according to a timeline, frequently we just get this mission activity. Some people, you know, it looks like a function. I send a command, and I deploy the solar arrays, whatever they are. Why I asked the question earlier on about the use of the word thread is because we've heard people use the phrase thread in software development as a way to do tests, and they thought it was Like You Fly, and people put together scenarios and they think that's Like You Fly, and it kind of is, but it isn't all of what it is. There's a third pyramid we discovered, but I didn't want to really bother you here with, and that's the supplier. That is, if you're acquiring a system and you're getting some code from some other outfit, and you haven't told them what the mission is, you know, maybe it doesn't matter to them, but maybe it does. That was part of it. So when I talk about a mission and the phases of a mission, this is what I'm talking about. We start really from T0, or just slightly ahead of T0 if we're loading up flight software patches and databases, things like that. We go through Ascent. We sometimes do orbit transfers. Sometimes a lot of times we have an initialization phase. We do some checkout, and then whatever the nominal ops. That's a notional way of organizing a mission. Some missions are going to be variants of that, but that's the kind of timeline and set of the basis for the kind of Like You Fly test we're talking about. This is another representation of a timeline, and what it illustrates is that different organizations that are participating in a flight have their own timelines. So the space vehicle might be on one timeline. Its payloads actually could be on a different timeline. We have vehicles that have their own mission, and they host another little payload, and they don't know what's on that payload, and it does its own little thing. We have the ground has its own cycle for mission planning. We have users who may interject themselves into this. We have people who can task a mission to do a particular thing. So everybody has their own timeline. They all matter. This is a graphic representation of a launch timeline. That Ascent means something to a launch vehicle person, and it means something very different to a space vehicle person. The launch vehicle is going to do what it's going to do on a particular timeline. It's got to turn on engines, turn engines off, get rid of stages, get rid of fairings, and all like that. The satellite is sitting there doing something else. Most of what it's doing is, am I there yet? Is everybody okay? Are we there yet? But sometimes they do something active, and we have had problems with vehicles. They get thrown off the booster, and they're not right, because this Ascent thing, which a lot of times in tests just gets jumped right over, you know, like, I'm sure it's going to be fine, without doing very precisely what is going on there. So we do start at the beginning of this yellow brick road. This is just a chart to summarize what I started to say before, that a lot of what's in our process here is not just about what the vehicle is intended to do, but about the kinds of flaws that we have put into these systems that are just waiting to be discovered, and you would really like to find them before you fly. Can I have a show of hands? People here familiar with Mars Odyssey, even maybe more than I am? Yeah, so I don't want to tell you your business, but we met with the chief engineer out of Odyssey after having seen those failures in '99, the back-to-back climate orbiter, polar lander failures. And one of the things that came out of the Mars Odyssey, project was this thing that says, not only do you have to do this forward-looking kind of test, but you actively have to understand where you can introduce failure. You can introduce it at the code, you can introduce it at the software-to-software interface interaction level, you can introduce it at the software-hardware level. You need to understand where they can be introduced, and you have to know what constitutes failure for the mission. And so when I talk about mission failure, I don't mean I can't deploy the solar arrays. I don't have enough power to do the mission, whether it's the solar arrays being out, or the command never got to the solar arrays, or the software never got around to processing the command because it's hung up on some infinite do loop. Whatever that is, you have to figure not only what the mission failure is, but then those paths to failure. And you need to go looking for evidence that those flaws are not there. So that is a message that we took out and we stuck into this process, because a lot of what we're going to have to do is look for the flaws, because we can't do a lot of the active testing. So here's back to that example of a timeline for a spacecraft, and there are places, obvious places, where the software is either an active contributor to the flaw, or it's perhaps an innocent bystander, but it's going to get blamed anyway. I do have to tell one story, just because it's just one of those dirt stupid things. And it illustrates kind of this hardware-software sort of thing. There was a flight back, a launch back in around 1990. So somebody mentioned earlier on the Ariane 5. Ariane 4 was such a commercially successful launch vehicle, with the model that says, let's take 2 satellites to geo orbit, and pretty much the cost of the mission is wrapped up in what they charge the first satellite and the profits in the second satellite. It's a really nice business model. And there was, in the late 80s, this projection that there was going to be lots and lots of commercial flights, and so the American rocket people decided they wanted to get in on that, and the people who made Titan decided that their Titan II could be a commercial vehicle, and they launched one of these with 2 satellites, worked just fine. The second launch had only 1 satellite, and because it was kind of big, and there really wasn't room for the other one. And so if you picture it, if this is the rocket, and you had a payload, and you had a second payload, as a second satellite on top, and you get to geo, you have to get rid of that one on top. Number 2 goes for, the one on top is number 1, maybe, and you get rid of that. And the one next to the booster is number 2, and there's only 1 satellite. What number is it? I mean, that's how dirt stupid is. So this went down as a miswire on the hardware side, but it was also a mismatch, because if somebody would have told the software guys, hey, we miswired that, can you fix that? The software guys, I'm sure, would have been able to handle that. So there's this little deal here. Where can you find these kinds of flaws? And sometimes the flaws don't get introduced until very late in the game. Guys, can you count to one? That's one of my favorite ones, until I met somebody whose payload it was that never got separated from the booster. Okay, so to do like you fly, what you want to do is, as I said, map elements of the mission to like you fly tests, and to do that is really a three-part thinking process where you identify potential candidate like you fly tests. You do an assessment, says, can I do this kind of a test? What do I have to have in terms of resources? What do I have to compromise on to do the test? Is it better to do it on the space vehicle? Is it better to do it on a test bed? So that's the kind of assessment activity. And then I allocate it. I decide to, yes, I'm going to do that test, and we're going to put it somewhere where we can execute it. We recommend doing these tests driven by your timeline. So here's how you identify potential tests. Or you might do something in that first couple of days, something that people hear the phrase day in the life test. Everybody familiar with that? And we've had day in the life test says, oh, okay, day in the life. So we can do what, 12 hours? How about 4 hours? Go, no, how about days in the life? Because that's what goes on orbit. How about those first critical ones? How about, a lot of times we do a day in the life late in the mission, and that's fine, normal ops. You always want to know that you can do the actual mission, but you don't want to forget about you have to get there. And once you keep in mind that the failures usually show up early, you want to be doing that. You might want to do transitions, going from adding on one payload to the second payload. You might want to do something that involves stressing the ground system, the interaction. And there's a few more of those, which this is an illustration of how you would identify different like-you-fly tests to do different objectives. Did I just do something? Oops, I think I did something bad. Okay, sorry about that. Operator error. Okay, so you can go through this exercise of starting very simply from the beginning for T0, and what kind of tests would you want to do, and where would you want to do them? So sometimes you might want to do something, I don't know, with an actual space vehicle, and sometimes you might want to do it right there on a test bed, especially the software test bed. Do it as early as you can. That's called risk reduction. And sometimes it's going to be really the only place that you can get certain kinds of errors flushed out. So you may have more opportunity on a test bed to get more test cases. So you have to balance out what you're going to do where, and how much of the timeline are you going to do. Those are the kind of decisions that you make for assessing and allocating. So you might take that Ascent test and do it at the vehicle level, and you might do a different Ascent case at the software level. You might do the same one just to make sure that it works. And you might do a part of the mission phase. You might want to just look at a transition. You might want to then do the whole Ascent as a whole phase. You can do it in a few hours or less. So these are the kinds of questions you need to ask about what kind of tests do I want to run that look like the mission, and where am I going to allocate it to? All the folks who are involved in the software at least the level of, beyond the code into the level of executing functionality of the software should be involved in these decisions. There's also a concept that we came up with that we call the test architect. If you think about tests like you fly from a airplane perspective, the person who's really responsible for running the test of an aircraft are the guys who are like the people who are going to wind up using it. That's why we have an outfit out at Edwards where they do these flight tests that really look like missions. And we were trying to decide, what's the equivalent for space that we could talk about. And as close as we could come up with a test architect, that's somebody who usually in the customer of the system that's being handed over should have some say as to what they want as evidence that the product can do what it's supposed to do. So we have this thought that if you're doing a system level test, that somebody from the customer team ought to be involved, if not actually being the architect, at least working with an architect at the system integrator level. If you are accepting, a TOCT means Total Operations Chain Test, which is ground and space. If you're doing a lower level test, say you're doing something that has to get integrated onto a payload, it should be the person who's like the PI, principal investigator, who's going to have a say in that. And then that person would say, what is the operability part that has to be shown in that test? So this process is not just about what you do, but it's about who does it. Since time is a little short, I won't spend too much on this, but we did want to emphasize that like you fly tests are representative of an actual mission timeline. So we usually are talking hours, days, and possibly weeks in the life. And a lot of the duration comes about because of software. It's one thing to talk about the first time event, and that's really where a lot of failures occur, but there's the other part, which is the accumulation error, or the kinds of things you guys have been talking about all afternoon. Things that you can see building the code. You can check for a lot of these errors, but just because you check it there doesn't mean it doesn't get reintroduced because of the way the software interacts with the rest of the system. So you need to ask those questions. How long is it going to take for me to show that I don't have an overflow issue, I don't have a buffer that's going to be overwritten, that I don't have a counter that can't count? So these tests need to have that software insight as to how you actually design the software, where you might have those breakpoints. So a lot of the answers to these questions about how long is enough will get informed by not only what the mission activity is, but also by the way you designed and implemented your software. We talk about characteristics that you have to include in a test, and one of the reasons we made a point of doing this was when we first started out thinking about how do you do tests like you fly, and how do you assess a test program for its fidelity to like you fly. And a lot of the conversations that we had were typically with hardware people who would say things like, well, we send flight commands, and this is somebody who's in a factory test floor saying, well, we send flight commands and we get flight telemetry, what else is there? And he said this with a straight face, not understanding that, of course, as a test conductor, he would never send an actual flight command or use an actual flight database or have the last patched software version up there, and didn't understand that there's more to it than a command or looking at telemetry. It's all these other things. So yes, you do commanding, yes, you look at telemetry, but you also look at timelines, you look at configurations. You look at especially the integration level, because you can add on errors as you add on stuff. Okay, I am about out of time, so I'm going to just get to, oh my God, I was only one chart away. So the bottom line here is that Test Like You Fly really is a process that is both a system engineering aspect, and it involves the software engineers and software developers in ways that are a little bit different, but you can use that mission perspective to help you decide on what test cases that you might want to run out of the hundreds that you could run. Okay? And I think that's all that I have at the moment, and if anybody has any questions. Oh, there's, let's see, do I have? Yeah. So this is, it was in 2008 that we had that Mission Assurance Improvement Workshop where we had we had people from JPO and APL and NRL and all the majors, and out of that came this thing is called a tour that can be shared with government people and their contractors, and that's like an annotated tutorial of what you've gotten just a little brief segment of. We are about to publish something that looks like text, and I'm hoping to have that soon. I've been saying soon for about 3 months. And we have another, if anybody's interested, we can get them these things. They're not available to be put on the website because most... You're not available to everyone. There are some limitations. On this tour is cleared for public release. Actually, this one is not. I think the Aerospace Library makes every effort to distribute those things. Yeah.
Okay, well, thank you. Are there any other questions? Yeah? Yeah, in my experience, I've only seen requirements flowed to us about what the thingy is supposed to do, not how the thingy is supposed to be tested. Maybe we're not at a high enough level because we're just doing software, hardware level integration, not a full system. But it seems like that should be in the very statement of work. Absolutely. Is that... Absolutely. So are you preaching to the choir, or are you, is that such a thing, or is that just, it would be a good idea if that did happen?
It's more than a good idea. We've had things fail that were, like this is a vendor thing, among other things, where a box fails on orbit, and it's because of something in the design was not comfortable with being duty cycled. And you go back to the vendor, and the vendor said, duty cycled? You never told me it was going to be duty cycled. If you wanted to duty cycle it, you should have told me, because I would have designed you something else. Yes, you absolutely have to know how it's going to be used so that you can do the best design work, and then you can do an informed test set. And it goes all the way down, I hate to say it, to the part level and probably to the unit code level. Because we have examples of those things that have escaped. Yes, so absolutely, people should be sharing with you the mission, because a geo mission and a HEO mission and a LEO mission and a planetary, they're all different. And they put different demands on the hardware and on the software.
No, I think everyone understands that. Everyone understands that, but it's just that it becomes prohibitive, saying, well, if I don't have to do this, if I don't have to spend this money, I won't. And unless you're told thou shalt, you might cut this corner, even though it would be a great idea.
So I'm all about saving money. My background, which I didn't really explain here, I spent 18 years in an outfit called Space Test Program. Anybody here familiar with Space Test Program? It was an R&D branch of what's now Space and Missile Systems Center that does R&D. We don't have much money, never had much money. You know, like a $50 million project was huge for us. And most of the ones that they today still put together are for $20 million. And we did $20 million 20 years ago. So these were cheap sats at the time. Now you can get something for $1 million maybe on these little CubeSats. But so this, I was doing the Like You Fly stuff for $1.95. You know, you just added on to the test that you were going to do anyway, but now you just are more clever about, you know, the test case. You say like, okay, I can't do 100 cases. All right, so why don't we do at least a few that look like the mission? You got to do them anyway. You got to do some.